Okay, great. Thanks very much, Antonietta, for that introduction. So I'm really excited to be here and to interact with you all. So the panel asked me to talk about how we use observations to improve modeling and outlooks. And so I'll give my perspective as someone who's been involved in the ENSO community and with building and evaluating a lot of the models that we use for coupled forecasts and projections at GFDL. So of course, ENSO is Earth's dominant year-to-year climate signal. Every 2 to 7 years, this pile of warm water in the West Pacific expands eastward, bringing with it the deep convection and rainfall, and weakening the trade winds, flattening the equatorial thermocline, and altering the global atmospheric and oceanic circulation. And these changes and their impacts affect weather, ecosystems, and economies worldwide. So it's really crucial that we predict and project it reliably. So we're working to understand ENSO's seasonal decadal predictability, assess its future ENSO risks, and predict changes in its dynamics and impacts. Now, models are really essential for this because the observing system is short and gappy and non-stationary, but at the same time, ENSO is also a really tough test for models because of its coupled, multi-scale, diverse, and intermittent nature. So we have this wonderful tropical Pacific observing system, TPOS, out there telling us what's going on in the Pacific, monitoring the ENSO evolution and characterizing the background state. And of course, we have satellites, we have in situ measurements from moorings, ships, and drifters that make up the backbone of this system. And we also have more intensive field programs involving aircraft and robots like the gliders and sail drones that we use during field campaigns. And also in the last decades, we've had these Argo floats that can surface and sample temperature and salinity throughout the world ocean, and including the tropical Pacific, that are also part of the backbone of TPOS. So of course, then we take these observations and then ingest them into our models at places like GFDL and elsewhere, and build data assimilation systems that can then create an estimate of the ocean atmosphere, the fully coupled global state that we then use to evaluate models and to initialize our forecasts. And these reanalyses, they use dynamical and statistical models. And what's nice about them as a modeler, they provide a full context for the observations. So they're global, gridded, they're holistic with co-located variables. They aggregate and harmonize these diverse observations. And so we use them a lot and like them because they're easy to compare directly with the models, but they have issues. So often they're short in duration, so you have a limited number of events to compare your model to. They often have spurious artifacts due to model biases and sparse and changing obs. And we also have some key variables that may be diagnosed in a lot of the products that are served to the community, in particular budgets for heat and momentum. Simulation increments are often not provided in high enough space and time resolution to characterize processes. And often there's incomplete accounting for a lot of the uncertainties. So even those centers that provide PDFs, often in the form of sort of Monte Carlo samples from ensembles of simulations, we often, these don't represent sort of a plausible range of the total uncertainty because of the absence of model biases in those estimates of the uncertainty. So these reanalyses often can disagree with each other and with independent obs, and make some kind of fuzzy targets for and biased forcings for model development. So another challenge for using OB to constrain models is the interdecadal modulation of ENSO. So here's looking at Nino 3 SSTs in the Eastern Equatorial Pacific, looking at those anomalies through time. And we can see that ENSO waxes and wanes over the last century. And then if we produce a model run, say using a pre-industrial control run, 20 consecutive centuries of simulation from this model, one of the GFDL models, we find that it can spontaneously generate, without any changing external forcings, no radiative forcings or global climate change going on, just the model running on its own, can produce 40-year epochs of hardly any ENSO variability with very strong ENSO events, 5 or more years apart, very skewed toward warm events, or with very regular symmetric events, warm and cold every 3 years, or with a little of everything. And the timescales of this modulation can be extremely long. We can go 2 centuries with mega ENSO events continually, followed just a century later by 2 centuries of hardly any ENSO events. We can also generate a century from this model that looks a lot like the observed realization over the past century. So this poses a conundrum for model evaluation because, first of all, it's expensive. You have to run a model a long time in order to characterize its ENSO behavior, its emergent ENSO behavior. And even more a challenge is the fact that we only have one observational realization of what has happened. So it's not clear that what we've observed over the past century has been fully representative of what ENSO is capable of, and it's a sufficient target for model development. Another challenge is the numerous feedbacks that are involved in ENSO. So just to give you a schematic overview. So here's Indonesia in the west, the warm pool, South America in the east with the cold tongue. We're looking over the top 200 meters or so of the equatorial XZ plane. And so let's say we have an SST anomaly in the Eastern Pacific, a warm SST anomaly. That will induce wind stress anomalies in the west, such as westerly wind stress anomalies that weaken the trade winds, that then acts through equatorial ocean Kelvin waves to flatten the thermocline, deepen the thermocline in the East Pacific, warm the subsurface temperatures that then is conveyed to the surface by upwelling and warms the SST, a positive feedback. And this is called the thermocline feedback. And what's interesting about this thermocline feedback is it has two time scales. It's got a fast time scale associated with this relaxed slope affected by the equatorial ocean Kelvin waves, and also a slow delayed negative feedback that comes from off-equatorial wind stress curl and Rossby waves, which I'll discuss in a moment. So interesting non-local effects associated with this displaced wind stress and these propagation time scales associated with the thermocline feedback. The wind stress anomalies also generate zonal current and upwelling anomalies and mixing anomalies that we group into the zonal advective and Ekman feedbacks, another positive feedback typically for ENSO. But there's also, so these feedbacks together are called the Bjerknes feedback loops. And we also have damping from surface heat fluxes, evaporative cooling, cloud shading, and also damping from tropical instability waves that stir in water from off equator. And then this whole set of coupled feedbacks is itself then driven by stochastic forcings, mainly in the form of westerly wind events in the western equatorial Pacific, that themselves depend on the warm pool extent and the SST anomalies in the equatorial zone. So you can see we have a complex set of feedbacks, and ENSO emerges as a subtle balance among these various feedbacks, and all driven by noise that is state dependent. So it's a real challenge to model and also to observe. Now, I'll focus in particular on a question that Antonietta asked me to highlight, which is that this non-locality of many of these feedbacks. Just to give a really sort of prime example of this is this theory of the recharge oscillator of ENSO that Fei-Fei Jin developed in the 90s. And so again, we're looking in the sort of XZ plane here. And if we consider this warm SST anomaly at the onset of an El Nino, that is associated with these westerly wind anomalies in the West Pacific. These then generate this rapid downslope of anomalous thermocline toward the east that feeds back and to warm the SST. And so that's that fast response that itself is non-local. But in addition, we also have at the poleward flanks of this equatorially confined westerly wind stress anomaly, we also have a cyclonic curl that generates Ekman suction, poleward surge transport that discharges equatorial heat content in the upper ocean poleward. And so what that can do is gradually shoal this thermocline as that upper ocean heat content leaves the equator. And then that can eventually terminate this warm event so that we end up with no SST anomaly in the East Pacific. But we're not back to where we started before the El Nino because this equatorial heat content has been discharged, the thermocline has shoaled. And so we can often overshoot with this shallow thermocline and cold subsurface temperatures into a La Nina event with cold SST anomalies in the east, easterly anomalies in the West Pacific that generate anticyclonic curl and equatorward convergence of upper ocean heat content that then charges up the equatorial zone with heat content, and we end up with a deeper thermocline in the East Pacific that can warm the SST and the cycle can repeat. So the point here is these non-local feedbacks are really important for understanding the processes in the Eastern Pacific. We have non-locality in longitude and in latitude associated with the wind stress curl, and also in time. So we have these delays, in particular with this off-equatorial recharge-discharge process that can take 6 months or more to feed back on the equatorial zone. So to constrain process studies, for example, if you want to do a process study in the Eastern Pacific, you really need to know the basin-wide winds and its meridional structure. And this, in turn, is also modulated by the seasonal cycle that helps control the time scale and the seasonal phasing of ENSO. So that's just one example. Many feedbacks in this region are non-local or non-linear. They affect ENSO's asymmetry and irregularity, its seasonal timing, its predictability, and extremes and impacts. It affects its interactions across timescales and with the background climate, including model biases in the background state and future climate change. So process studies require dense sampling to capture these nonlinear extreme events that have an outsized impact on the mean state and on the character of ENSO, and also capture the large-scale context, including the basin-wide winds, to capture these non-local effects. So just some examples here of some of the nonlinearities in the system. We have tropical instability waves that preferentially damp La Niñas compared to El Niños. We have the subsurface nonlinear dynamical heating that can often preferentially amplify La Niñas relative to El Niños, biophysical feedbacks. In addition, we have these non-local effects. So I mentioned this one associated with the sort of recharge-discharge process and the two timescales of slope and poleward discharge of heat content. But we can also get similar effects from biases in our model. Say we have, for example, in one of our GFDL models, we have excessive rainfall and atmospheric latent heating off equator that heats the column, generates cyclonic surface wind stress, Ekman suction, sort of discharge in the upper ocean that can shoal the equatorial thermocline. So an off-equatorial bias affecting the equatorial thermocline. And similarly, problems with the solar absorption, the depth of solar penetration into the water column associated with, say, excessive chlorophyll off equator, or too little vertical mixing and a parameterization can lead to off-equatorial deep cooling that works its way equatorward and shoals the equatorial thermocline, feeding into an equatorial cold bias. And there's many other examples that we could discuss after the talk if you like. So it's a real challenge, and not surprisingly, there are some common tropical Pacific biases that develop in these couple GCMs, and these stem from errors in our parameterizations that then amplify due to the strong ocean atmosphere feedbacks in this region, the same ones that are involved in ENSO. And so we'll often get, equatorial cold bias, this Eastern Pacific warm SST bias, excessive trade winds in the west of this cold bias, a double ITCZ, weak tropical instability waves, and then this feeds into problems that we see in models with weak ENSO air-sea coupling between the SST and winds, insufficient damping of ENSO, and not enough diversity and asymmetry of events, and shifted teleconnections, which really affects our forecasts. So to address some of these issues in models, a major thrust of the Tropical Pacific Observing System 2020 project, TPOS 2020, over the last several years, has been to improve models through both improving our backbone observations that we use to monitor the Pacific, and also detailed process studies that build on this backbone to give us a better picture of the processes. And so there were three major TPOS reports that we produced as part of this effort. I was involved in all of these. So all of them really emphasize the importance of and motivation for in terms of model development for these advances in the Tropical Pacific Observing System. So we called for better sampling of key climate regimes, in particular those linked to our coupled model biases, forecast errors, and ENSO. And the foci were really on the equator, on the coupled air-sea boundary layers, air-sea fluxes, convection in clouds, and upwelling and mixing in the equatorial zone. And so some of the key recommendations from these reports were first to increase the density of observations both in the meridional direction near the equator, for example, in the heart of the cold tongue, and also the vertical density of these observations for both temperature and salinity, and also currents in the vertical. And called for more surface fluxes, for example, from supersites at a few of these tau locations, and better instrumentation for surface fluxes throughout the moored array. More measurements of currents at more sites along the equator in particular, as well as off equator, in particular key regions like the cold tongue, and vertical measurements of salinity as well. Extensions of these mooring lines toward the ITCZ and SPCZ regimes to characterize those. And one of the advances that we've had in the modern observing system is that we don't have to rely on the moored array quite so much for the mapping capability it had to provide in the 80s and 90s. Now that we have a lot of Argo observations, and there's a proposal as part of TPOS to double the Argo density in this region. And also from satellites, we have satellites measuring SSH, SST, and also the surface wind stress, so they can take on some of the mapping role that the array used to provide. And so we can refocus the moored array on some of these key physical regimes that models do very poorly. For example, the equatorial cold tongue regime and the West Pacific warm pool edge. And so the idea is to augment this backbone set of observations with intensive field campaigns. And So there's kind of two approaches that we take in model development to using observations. So one is an indirect approach where we tweak parameters in the model and evaluate the emergent simulated climate and variability. And this is quick to do, but it's often challenging to attribute model biases to specific pathways because the solutions are often confounded by non-local coupled feedbacks and error compensation. And of course, an alternative approach is to use direct a way of evaluating detailed process representation against co-located observations. The challenge is that these test cases have to be really well constrained to inform us as to how to develop these parameterizations that's sufficiently representative in order to have comprehensive observation parameterizations. And this is a much slower process. It can take years, but it's more likely to work across diverse climates and events for the right reasons. Now, a challenge, of course, there is that as you improve one process, that might unmask other biases that you didn't know you had. And so iteration may be needed to develop a coupled model that works across diverse regimes when all these components interact. So as part of the TPOS effort, two of the process studies were proposed that really bubbled to the top, and they aim to really support more of these direct approaches to process evaluation in models. So the first is this air-sea interaction at the eastern edge of the warm pool, EEWP, that's focused sort of around the dateline region at the eastern edge of the warm pool, one of the strongest zonal SST gradients in the Pacific. And this is a region with really strong deep convection that dumps a lot of rain on the surface. And sometimes you get these events with very shallow, fresh lenses that generate strong salinity stratification in the West Pacific and an intense barrier layer below it. And this is important because it shoals the mixed layer in these regions, and you can get rapid acceleration of this relatively thin layer at the surface when you have westerly wind events, for example, either during an MJO or at the onset of El Nino. We think these may be important for ENSO's behavior and predictability. So the focus here is really in that sort of XZ plane along the equator in the West Pacific and measuring a number of key variables there. The other key process study was Pacific upwelling and mixing, act to couple the atmosphere and thermocline. This was formerly known as PUMP, Pacific upwelling and mixing processes, but we're trying to include more of the atmospheric side too, looking at the marine atmospheric boundary layer and clouds and so on. And this is really focused in the sort of YZ plane. So here you're going from south to north and vertically over the top 200 meters or so. So in this region at the equator, we have this strong EUC heading toward the east, strong south equatorial current heading toward the west, and a strong vertical shear that generates a lot of vertical mixing in this region, destabilizes this zone. We also have strong upwelling and poleward movement of the Ekman currents driven by the surface trade winds here. And we also have intense tropical instability waves that stir across these strong fronts at the northern and southern flanks of the equatorial cold tongue. And so the sort of key issues here are mostly oceanic, but also interactions with the marine atmospheric boundary layer and clouds that are they're tough to get right in the models. So these regions really strongly interact through the winds, the currents, the SST, and the thermocline. And so these process studies are really complementary, and we're hoping to have both of them going, if not contemporaneously, at least have some overlap between them so that they can inform each other through these interacting aspects. So in preparation for these field studies, the NOAA CVP program funded a couple of waves of new projects that focused on what TPOS should measure to improve understanding models and predictions. So there are 8 projects funded a few years ago that have completed, and some new projects that were funded for this year and the next few years. And these range in scale from very high resolution regional models of coupled boundary layers, looking at fluxes and waves, studies with Otis data assimilation and OSSIs to test different observing platforms, to improving mixing in regional ocean GCMs and constrained by forcings at the surface. And we're kind of at the high end of the food chain, looking at how these can feed into improving the coupled GCMs that are relatively coarse, but that we have to use for forecasts and projections that can, we can inform their parameterizations based on what we learned from these studies and from the TPOS new backbone observations and field studies. So this project we have at GFDL as funding a new brilliant postdoc we've hired, and she's doing a great job. She's been with us for about 6 months. And the objectives of this project are to improve the diagnostic hierarchy for CGCMs, to advance understanding of the equatorial Pacific role in climate and ENSO, to attribute and reduce the biases in models in general, but in our GFDL models in particular, and also inform the TPOS strategy using some of the broad scale information that we can gather from these coupled GCMs, the sort of broader context in time and space. So some recent progress, just a quick summary. So we've run a number of ensembles, 30 members each, from our free running model that we use for our forecasts and projections, a nudged version where we constrain the SSTs and wind stress to evolve-like observations, flux-adjusted version that corrects the background climate, ensembles from each of these. We've looked at various atmospheric resolutions. We find that it strongly affects many of these processes I've been talking about and affects ENSO. Running with bias corrections also not only improves our ENSO patterns and forecasts, but also tends to amplify its projected future rain extremes in response to climate change. We also have worked with looking at using this flux-adjusted framework to look at the intrinsic biases in the individual components. We found that our atmospheric GCM generally tends to produce too much convective precip, so that leads to, in part, to our excessive equatorial easterlies that amplifies when we couple. And our ocean GCM tends to be too viscous near the equator, which reduces its transient shears and mixing, leading to strong thermal stratification in eastern equatorial Pacific upper ocean, especially during boreal autumn and La Nina, which may involve a role for underestimated TIWs at the resolutions we typically run in these coupled GCMs in the ocean. And we're also experimenting with model analogs as a way of forecasting ENSO and a way to inform us about the potential predictability available from a new model that we've developed, any new model that we develop through the development cycle. And also we found that these actually can match the skill of NME forecasts based on some work that we've done with our PSL colleagues, including Matt Newman and Hui Ding. Brandon Reichel at GFDL has also been working with sort of the ocean-only context in the various configurations ranging from 1D to global, using Argo measurements and LES simulations from Dan Witt. And he's experimented with the vertical layers, density, with the vertical mixing schemes, and found that he's able to produce a much better diurnal cycle and near-surface stratification, a deeper thermocline that improves our biases. And we've run these in our ocean GCMs and coupled GCMs, and they're looking very good so far. So we're really looking, we think they're very promising, and we're working on finalizing and analyzing our high-resolution SPEAR High 25 model with quaternary atmosphere and ocean that we can use to leverage some of these improvements we've seen in the ocean side. And finally, I want to touch on some of the community metrics that we've developed for our ENSO simulations in the broader community in collaboration with the CLIVAR Pacific Region panel. And this is a diagnostic package developed in Python that we use to diagnose ENSO behavior. So here's an example, the El Nino life cycle. Say you look at the evolution of El Nino, a typical El Nino in your model, the black line compared to observations in red, and then you can derive a particular metric for this kind of diagnostic, say the RMS error over this plot between the model and the odds. And then once you have such a metric, you can compare that against other metrics or other models across the CMIP archive. And this is an example portrait plot from CMIP. And we can also provide a multi-model context for our coupled GCM, say in green relative to the full CMIP ensemble in gray, or particular observations in red. And what I think is really exciting is that we can use these multiple metrics to discover connections among them and find emergent constraints for how, for example, historical biases in model solutions and background state are related to future climate sensitivities and ENSO sensitivities of future change. There's an example showing intermodel correlations among metrics, and there are lots of interesting relationships here that can give us information on what the models may be doing right or wrong about ENSO and its future sensitivities. And we're providing this package it's available to the community via our website, both code and data sets. And we're providing it to the broader community through a number of evaluation tools, including the PCMDI metrics package. So I want to finish with some potential ideas that we can discuss that the PSMI panel might be able to interact with us on. So one is engaging with and advocating for TPOS, so helping to develop these process studies, and also aiding in the broader coordination across agencies and panels, both in the US and internationally. advertising these ensometrics, using them yourself in your work if possible, contributing to the package, particularly on the process side, and recruiting, help us gather resources for it. So one is, we're working toward improving process metrics through this CLIVAR Pacific Panel working group on conceptual models of ENSO. And we're also trying to improve some of the aspects of evolution and prediction metrics of this package, and also looking at these emergent constraints I mentioned. We also need advice on what observations to use. What are the latest, greatest observations? What are the pitfalls and strengths of various products? And also, again, gathering resources to help support this effort toward developing ensometrics. Another is proposing frameworks and benchmarks for GCM. So one is this model hierarchy idea where we say use partial coupling and observational constraints in models. We look at across different resolutions and complexities. And we also use intermediaries between OBS and GCMs, for example, using large eddy simulations, high-res OGCMs, and so on, and AGCMs as intermediaries between the detailed observations and the relatively coarse resolution but global coupled GCMs. And also developing comprehensive model test cases with reliable observational targets. It's really important to get at the detailed processes and their broad scale context. For example, using the MIP framework would be one way to do that. And also rallying reanalyses and reconstructions. So it's really useful to aggregate the available data sets for modelers. And there are a number of efforts in the community to do this. And I think a particular very helpful one is this NCLAR Climate Data Guide, which integrates community guidance on what the strengths and weaknesses of these various data sets are for model evaluation. It'd be helpful if the panel could engage with surveying and intercomparing and reconciling existing products, what are their strengths and weaknesses, and offering better constraints for processes in particular, especially for budgets in the ocean and atmosphere, for heat, momentum, moisture, and so on. And also characterizing the PDFs, which are so important for these nonlinear feedbacks. And also reanalyzing better, longer, and more often using the latest models. And then finally, helping to coordinate resources in general. For example, perhaps proposing climate process teams or CPTs in various aspects that are critical for ENSO, and also pushing advanced computing so we can run with high resolution, run creative experiments in a robust way, which is expensive. And then also helping to recruit and train the diverse brains that we'll need to solve these problems. Thanks very much.
Hi, Andrew, for your very nice talk.
Sure.
So I have a question about this, the model bias in recent SST trend over the equatorial Pacific. What can you, what do you suggest? How can we better understand, this important bias and connect and process level, model efficiency? Yeah. Thank you.
Sure. Yeah, so thanks for asking that. I had a bunch of slides I had to drop for time, but so what Ming's talking about is, if you look at the CMIP5 projected changes in tropical Pacific climate, the models, most of them tend to show this kind of response where you get a sort of El Nino-like future change where the whole tropics are warming, but you get more warming in the eastern equatorial Pacific than off equator or in the west, and a shoaling of the thermocline, weakening of the trade winds, and so on. And this is really crucial for how ENSO responds in the future. Unfortunately, the observations don't seem to be heading in that direction. They seem to be showing, if anything, a slight cooling of the Eastern Pacific relative to the off equator. Although there are sampling issues we haven't observed maybe quite long enough, but if you look at ensemble simulations of historical simulations, the observed realization is kind of right at the edge of that. So there's a pretty strong suggestion that the models may have some problems simulating these long-term trends. And so there's a number of different issues that may feed into this. So a few that we can highlight. So first of all, the models tend to do one of these feedbacks that gives a sort of El Nino-like future change pretty robustly. So one is you get this moistening the atmospheric boundary layer and also this increased stability of the troposphere that tends to weaken the convective overturning and weakens the trade winds. And so that tends to bias you towards an El Nino-like response. We think this is a real feedback. We don't know particularly how strong it is. But then there are a few other feedbacks that may be underrepresented in the models. And this is from a recent review paper that we did looking at these feedbacks. And two in particular are this ocean dynamical thermostat. So in the eastern equatorial Pacific Ocean, near the surface, you have continual upwelling of cold, relatively unperturbed water from the deep. And so if you move forward into a future warmer world where the surface is warming, that warming in the eastern equatorial Pacific is inhibited as that sort of surface warming gets flushed away and replaced with relatively unperturbed cold water from the deep. And so that can tend to give you, if you impose warming from above and inhibit it from below in the eastern equatorial Pacific, that can tend to give you a La Nina-like response. And there's some reason to think, including from some of these studies I was talking about with looking at the biases in our models linked to the background cold biases and so on, that we may be underestimating this ocean dynamical thermostat effect. And a second key issue is, say, representation of deep convective clouds, and in particular, cirrus anvils in the Western Pacific. So we may not be representing the future change in anvil contraction. The contraction of cirrus clouds, which has radiative effects, may increase the long wave cooling at the warm pool edge, and then feed into a more La Nina-like response. So if we're not, say, representing this, because of inadequate resolution, the say convective aggregation or lateral entrainment of dry air into these plumes, and we're unable to represent the sort of height and extent of the anvil clouds, we may be underrepresenting some of these things. So all these are really crucial issues. And so, it's really important going forward to try to assess the impacts of those on ENSO.
Great, thank you, Andrew. Maybe one more question. I think your divisions, some people have already done those flux adjustment experiment. Do you recall if in those experiments the SST trend bias getting better? Is that just which signal have a hypothesis basically suggests a climatological co-bias could be the cause? I don't know if you have looked at that.
Yes.
Oh, that's great.
I couldn't have set you up better. So we did look at this in SPEAR, which is the model that we use for our forecasts and projections these days in our division at GFDL. And so we looked at this in this model. So where we have the observed tropical Pacific pattern and these common biases I showed. SPEAR has them as well, the cold tongue bias and warm bias against Peru. And when we flux adjust, the aim of the flux adjustment by design is to reduce those background climatological biases. So the flux adjustment does that. That's sort of present day climate. And then if we look at how El Nino behaves in that present day climate, if you look at the observed precip response during El Nino, we see this eastward shift of rainfall into the equatorial Pacific, eastward and equatorward shift. The convection shifts eastward and equatorward. And often in a lot of models, including SPEAR, this shift is inhibited. It doesn't shift far enough east and far enough equatorward. It tends to be displaced westward of where it should be. And this affects a lot of the teleconnections as well. Mm-hmm. When we flux adjust, this gets quite a bit better. We are able to get the deep convection farther east. Even though the SST anomaly patterns haven't changed much, it's the background SST gradients that temper this response. So if we have less of a cold tongue bias, we have the relative SST during an El Nino event gets close enough to the convective threshold that we're able to generate convection in the eastern equatorial Pacific. And what's interesting about this is it also affects our future behavior. So if you look at the sort of Nino 3.4 rain spectra in this model, so observations in black, you can see that this model, again, we saw this over here in the sort of central equatorial Pacific in SPEAR. It tended to produce too little rainfall and too little rainfall variability in that region. It's way underestimated, very dry and quiet in that region. But when we flux correct in sort of historical simulations here, we see that improvement where we're able to get it closer to observed. And if we move forward into the future, we see the strengthening of this ENSO variability associated with the SST anomalies. Now, when we flux adjust, we get a much stronger response of that future ENSO rain anomalies. We get bigger rainfall extremes as we have less. So the flux adjustment increases the SST in the cold tongue, which enables the convection to shift eastward more easily during El Nino and in the future. Now, the thing to note about this is this goes counter to some of the arguments made by Richard Seeger and so on. but it's not really counter. It's actually sort of complementary. This says that if you correct the SST biases that emerge in the coupled GCM as formulated with its resolution, relatively coarse, it is missing some of these processes like the ocean dynamical thermostat not being strong enough, or the convective anvil cirrus not contracting enough, that the model itself amplifies ENSO even more in the future when you correct background SST biases. And so maybe if we corrected those background, process biases in these models by, say, running higher resolution, improving our parameterizations, we may see an even stronger effect with, weaker future change in going forward. So there's a competition between the sort of emergent biases and the processes that are involved in future climate change that condition the future change in the SST gradients and ENSO behavior.
Thank you very much.
I have a very quick question just about these experiments.
Mm-hmm.
How do you do the flux adjustment for future projections?
That's a good question. So these experiments are just using the same flux adjustment that was required for the historical simulation. So it's just asking if we take a model, which in this case includes a flux adjustment to correct the climatology relative to historical observations. Going forward, if you impose a radiative heating anomaly, in the form of greenhouse gas induced warming and aerosols and so on, we're looking at the change relative to that system. But it's certainly true that the appropriate flux adjustment for the future could be different. So it's a sort of stepwise test, but it's not necessarily complete. But it is interesting that you can do these projections in different ways. You can do it, say, without the flux adjustment or with the flux adjustment and look at the difference. And there's clearly a sensitivity to those background SST biases. And there's also one reason to think that the nonlinearity might not be that strong is these flux adjustments are relatively small in the individual components. And once you sort of arrest the individual biases in the individual components, you arrest a lot of the coupled feedbacks. So those coupled feedbacks actually help amplify the good things you're putting in from the flux adjustment. So, even in the equatorial cold tongue where you have the heat budget has terms owing to subsurface advection on the order of hundreds of watts per square meter, the flux adjustments can be around like 40 watts per square meter. Still strong, but not a major part of the heat budget in that region. So yeah, a lot of really interesting studies that can be done, I think, using this framework to understand the coupled models and their response.
Had to find my unmute button. So great talk. This is actually the conversation you just had with both Ming and Antonetta actually covered a lot of the topics I had questions on. I just was in the middle of a qualifying exam earlier today where we were having a very vigorous discussion about this, issue with the observed kind of La Nina tendencies and the seeming incompatibility with the models. And I have a lot of questions around that, but I have to synthesize my thoughts. But jumping off of what Antonetta said, one of the things that kind of struck me, you mentioned that as part of the project you're working on right now, you're running kind of these free running spear ensembles, but then also these nudged and these flux adjusted simulations.
Right.
And I was wondering if you could provide a little more feedback as far as the nudged runs. So are you nudging to some sort of, because we talked a little bit about reanalyses, fuzzy, what is the target for the nudged runs, I suppose.
Yeah.
And then kind of the follow-up question is, at GFDL or in your have you found utility in things like the nudging tendencies or the increments in terms of diagnosing model biases and processes?
Absolutely. So let me address the second one first. So absolutely, those increments, we've learned a lot from analyzing those increments. So first, let me talk about how the flux adjustment and the nudging is done. So what we do, so we have a coupled model, coupled GCM, freely running global GCM. So that we do one simulation with that. And then we rerun that simulation where we nudge the SSTs with, in our case, a 5-day time scale toward observed time evolving. It's got El Niños in it and everything, monthly mean SSTs. So we're sort of dragging the tropical SSTs toward those observations evolving through time. So it's got El Niños and La Niñas, the same ones that appear in the real world are simulated and nudged toward in the model. And then we also are overriding the winds that the ocean is feeling. So the atmosphere is generating winds based on the SSTs it sees, but we don't use those winds in this run. We're actually overriding those winds globally with the wind stress at the surface is overridden with ERA interim wind stress. So the ocean, as far as it's concerned, feels and feels that the ERA interim wins and has a tight nudging to the monthly mean SSTs. So if we look at the increments that are required, so the increments here are the nudging term that is dragging the SSTs along toward the observations, and also the delta in the wind stress that's required to bump the AGCM generated wind stress toward the ERA interim wind stress. Those two increments are really informative. And one of the things that Shan Wu, our postdoc, has discovered is that those increments tend to do some obvious things. One is that the surface heat fluxes associated with those nudging terms tend to try to heat the equatorial cold tongue, for example, because we have that bias there, excessive cooling in that region. But they also do some interesting things where the wind override tends to weaken the wind stress in the West Pacific. And that turns out to be the lion's share of the corrective tendencies that are inputted in the model. The winds are really crucial. Those excessive trade winds in the West Pacific that are generated by the AGCM really are doing most of the generation of the excessive thermocline slope, upwelling, and cold bias that we're seeing in the equatorial GCM. So absolutely, those nudging terms are really informative. And sort of more broadly thinking about data assimilation in a 3D context, or 4D if you include time, those increments would be super informative as well. If we could sort of routinely output those, if the reanalysis centers could provide those analysis increments, and even more broadly, the heat budgets, for example, for the upper ocean, including those increment terms, that would be extremely informative to know what our best estimates of the heat budget are. And internally at GFDL, we have our own data assimilation system. And if you do assimilation in the same model that you're using to do your forecasts and projections and simulations, it's even more informative because the increments are telling you what your model is doing wrong. It's telling you specifically localized in time and space where you need extra heat or extra wind stress or some extra boost to give you a better simulation in that region. So absolutely, I think that's one of the best ways that we can confront models with observations is through those first guess errors and the increments or innovations that the analyses can provide.
So the question I have is, so this process study that have been proposed, and I think there have been this modeling going on for informing the actual field campaigns. Mm-hmm. So they are actually processes that occur at very fine scales. I think especially in the Western Pacific, the modeling studies are done at a very high resolution using model at high resolution. Right. So once we have either those modeling results and even observations of those processes, how can those results inform coarser resolution models? Can actually they help improve the coarser resolution model, or or just tell us that we can only get a good simulation of ENSO using very high resolution? So, I mean, what are the steps between this resolution kind of problem?
Right, that's a great question, Antonietta. So the approach we've taken at GFDL, in particular with Brandon's work in the ocean-only context, where you drive the ocean with surface fluxes and try to look at the simulation of ENSO and the mean state in the ocean-only context and compare against observations. So you run into challenges because you don't know if the errors in the model are coming from the model formulation itself, like the parameterizations, or from the forcings you're using. Maybe the reanalysis you're using to drive the ocean model isn't quite right. Maybe it has weak trade winds or something. So what we found to be useful is to look at the detailed processes at a variety of resolutions. So Brandon has used a few different approaches. One is using sort of 1D simulation. Let me go back to Brandon's slide here. So on this one. So, okay, so Brandon has a variety of different simulations with 1D models where he's got parameterizations that he can test using an idealized framework with a prescribed vertical shear associated with the SEC and EUC, and then test how those simulations using either a sort of state-of-the-art general length scale mixing that sort of performs very well in sort of the gold standard. He's able to reproduce that quite well that reproduces large eddy simulations that Dan Witt has produced. Very high resolution, sort of meter scale resolution right around the tow moorings and compared in detail with observations and mixing measurements. So there's kind of a sort of this idea of having the large eddy simulations and high res models serving as intermediaries between the coarse models that we run at these at the modeling centers that do forecasts and projections, and the fine scale observations that we would take with process studies. So, if you're doing a process study, you're going to have very fine scale measurements from UAVs and sail drones and moorings, and you'll have ships out there measuring maybe some armed sites at some island sites and so on, measuring atmospheric properties and aircraft measurements. And so those need to be placed in context through data assimilation at high resolution. And then also sort of our view at GFDL is we will kind of not feed directly off of those, but rely on the people doing large eddy simulations and high res simulations to validate their models against those. And then once those are validated, or sort of validated in certain contexts at least, we can then use those in a broader set of simulations from those models to then validate our coarse resolution simulations against in the sort of more broad scale context and global context. So I think we need kind of the whole hierarchy of models of different resolutions and complexities and different levels of observational constraint, both regionally and vertical level and so on, in order to inform the coupled GCM development. You can't really directly confront sometimes the coarse coupled models against the observations or detailed process studies.
Yeah, thank you.
Sure.
I had a variety of technical questions, which have all been addressed. And I had, so thank you. I think the sequence of questions was really good. And I had sort of a big picture question that maybe is a bit similar to Antonietta's. So you've talked about model hierarchy, both in complexity or resolution, and that's something that I think is really important. But I guess I was wondering, in terms of kind of your understanding of the topic or your expertise, what do you see maybe as where are the gaps in that sort of hierarchy or complexity workflow where we're still struggling to maybe have an intermediate, a test case that's complex enough to bring in the key processes, but easy or cheap to implement to test various things. So either something that's not easy because of the way that we traditionally build models or have our test case that are already existing, or if you can speak to what you've seen as a jump that, even though, maybe jumping from ocean only to coupled, where you suddenly see the feedbacks not kind of carrying through and where our understanding kind of break at that step. So either of those, if you want to speak about that.
Well, that's a great question. So I think what we found so far is that, first of all, there's very few constraints at the process level for those two process studies that I highlighted. So the Eastern Equatorial Pacific Warm Pool Edge, the process going on there with the salinity stratification, the acceleration of the surface layer, and how that interacts with the MJO and ENSO. So there was Toga Core, but it didn't really measure enough in that region at the right times to capture, and at the right resolutions to capture some of those features. And we can do that a lot better now with some of the autonomous vehicles and the enhanced mooring technology that's available now, and with the satellite data that we have, for example, the scatterometer wind stress and the sea surface height and SST. So that's a big gap. So that's in the West Pacific, and then in the East Pacific, a lot of those vertical processes are completely unconstrained. We have no idea how strong the upwelling is and how nonlinear it is, how strong how much the surface layer that, say, controls the cold tongue bias, the future climate sensitivity, all that stuff depends on intense upwelling events that occur intermittently that might not be well observed or captured in these relatively coarse GCMs. And so we really just, that's a huge gap. And that's actually the main reason that we proposed these process studies, that there's just very few constraints at all for any of those things. And so I think once we have those, then the various groups that I outlined here that are involved in these process studies funded by the CVP program are well positioned to then take those observations and use LESs and high-res regional simulations at, say, 1/10 of a degree or 1/12 of a degree to produce relatively accurate simulations of those regions. There are still some gaps in the vertical resolution. So even though a lot of groups have moved to high lateral resolution for these regional studies, the vertical processes are, in part because we don't have good measurements, are not very well constrained. So we don't know how sensitive the, say, vertical layering and the transient shears that develop in the water column are for generating upwelling and mixing. That's really crucial for the emergent cold tongue and ENSO behavior. So that's kind of on the detailed process side. In coupled modeling, I think the approach that we're taking at GFDL is really promising. So, one of the biggest changes you see when you do model development, often you'll have an atmospheric team, you'll have an oceanic team, and they're developing the models in their own silos, and they think they have a great simulation, but as soon as you slap those models together, you get a horrible emergent climate in that model. And so the approach we've taken over a couple of decades at GFDL is to couple early and often, and to include metrics for this individual process, for the individual component modeling teams that involve surface fluxes. So, the atmospheric team, the atmosphere model doesn't really care much about the surface wind stress. It's not a big constraint for the tropospheric solution, but it's critical to the ocean that is then going to feed back SSTs that are going to affect the atmosphere in a coupled model. So including those metrics for surface fluxes is a really crucial one. And similarly on the ocean side, the ocean may be able to produce a great looking SST in an OMIP configuration where you're driving it with, say, air temperatures that are prescribed from observations. But that's not really a good test of how well you simulate SST, because there's an additional sort of damping toward the observations there. So you're not really constraining the boundary layer simulation well. So I think a promising approach is to use this technique we're using in our division at GFDL to look at these partial coupling experiments of nudging, so where you're nudging certain timescales, say monthly timescales toward the observations, but you're allowing higher frequencies to interact, say the ocean and atmosphere interact on sort of daily timescales where you can allow convective shading of hot spots in the ocean so you don't get excessive runaway convection and processes like that. That's one promising way to constrain part of the solution and just gradually step toward coupling instead of just putting the models together and hoping for the best. And through the question from Colin, I think it really gets to looking at the increments and nudging terms, the additional heating and wind stress that you need in order to drag the model toward observations. There's a lot of information there that we can use to understand those interactions when we couple.
So, I mean, I guess you mentioned this on your, I think it's your, this one right here. So bullet point number 2, metrics. Can you just speak very briefly about the kind of user base of the metrics? This is something we've discussed occasionally, was not only applying the observations, but making them easier to use for model evaluation. That's not really a question. It's more just like, what are your thoughts on that? Where are we as a community, and where should we be going in the future?
Yeah, and there are several efforts in this regard. So I mentioned a few of them on this other slide here. Let's see, on this one. So in the community, there's a variety of different packages available. The PCMDI metrics package for intercomparing different models at sort of the very sort of 10,000 foot view of certain metrics, and the more detailed metrics and diagnostics that are produced by various tools like ESM Val tool, generally used in Europe, and also the tools that we use internally at the modeling centers. For example, at GFDL, we've developed diagnostics that diagnose thousands of different things that we can keep an eye on when we're developing these models. And so sort of internally at the modeling centers like GFDL, the challenge has been to maintain the expertise that knows that can both develop those metrics and also understand what they're trying to tell you. And there's a sort of continual training that goes on when you have new postdocs coming in, spinning them up on what those metrics are, trying to make sure that you're using the latest observational reference points, either reanalyses or other observations. So that's a challenge of making sure that you're updating those. And this is something we're actively doing right now at GFDL as we're anticipating the next development cycle of probably what will be called CM5 at GFDL, and the next model that will be feed into the CMIP and the IPCC assessments of first assessing what the diagnostics are that we have at GFDL at various levels, from process level all the way up to emergent climate variability and climate sensitivity. And it's a big effort, and it's such a big effort that it makes sense to not have the same effort going on separately at different institutions. You really want some kind of community consolidation of these, not to duplicate efforts. And so this ENSO metrics package that we developed with the CLIVAR Pacific panel is one effort to do that on the ENSO front, diagnosing things that are important for ENSO, like the background state, and then also ENSO behavior itself, and getting into the processes and teleconnections. And so I think there are a number of different efforts. There's been one on the MJO, and there are other efforts in the US and in Europe to develop these metrics. But I think the gap has been once those metrics get developed, there tends to be a lot of enthusiasm getting those developed, trying them out on a few models, but then taking that last mile to making them available at other centers, and then having those centers actually take them on board and use them routinely. That's been the remaining gap of getting the early adopters to test them out and give feedback. And that's something I think a number of us who have developed these various metrics projects have had the same issue. For the ENSO simulation, the ENSO metrics in particular, we have a really great set of software that's freely available. It's open code. The Python code is out there. We have test cases. We've published a paper on it. They're ready to use, but I think there's just a little bit of sort of initial barrier to somebody that they have to learn the package. So I think you need kind of maybe a workshop or a summer school to sort of teach how to use that. And we actually did that with the CLIVAR Pacific panel 2 summers ago. The ICTP in Trieste in Italy held a summer school in tandem with the CLIVAR Pacific panel. And we actually had over 100 participants in a workshop where we used this ENSO metrics package to train people on how to use it to evaluate models and intercompare their model with CMIP and so on. And so I think it was successful. What we still are sort of seeing how that's going to percolate through the community, but I think that's something that has to happen. You have to have somebody, get them over the hump of first, making sure the software technically works on their platform, and second, how do you interpret it scientifically to learn something?
Yeah, I think it's the black box aspect that may be a little hosting for people. So maybe.
And feel free to reach out if you have any other questions.
Yeah.
Thank you.
Bye-bye.